All right, we are continuing our sequence of videos. Our goal eventually is to get to Stokes' theorem and divergence theorem. Um, in, in the last video, we covered curl. We need those three items to get to Stokes' theorems and divergence theorem. In the last video, we covered curl and divergence. Now we're going to go into parameterizing surfaces, and we're going to also find the areas of those surfaces. After that, then we can look at a new video after this video for surface integrals. And then we'll have all the requirements to go into Stokes and divergence theorem. So let's get started. What is our goal in this video? Well, we will have eventually weird surfaces. I'm just gonna make something up. Pretend you got a really kind of weird surface somewhere in space. Yeah, so integrating with respect to this surface will be rather difficult. Eventually, what we want to do is figure out the integral of some function, whether that is a vector field or a regular function, with respect to S. I'm putting S for surface on that surface. So this would be S, I suppose. This is going to be difficult to do as is. You will have to, especially if this curves in many different ways. If it curves on the z-axis, for instance, then you have to really split this up into two pieces, the top and the bottom. And then if it curves again with respect to the y-axis, then you got to split it again. And it just gets it gets to be very, very messy if we attempt to integrate this surface as is. You have to split it up into a bunch of chunks, and then figuring out the boundaries of those chunks is already a lot of work, and then integrating each one of them individually is going to be some work. So the way we attempt to solve this problem is to come up with a transformation where we can take a rectangle and map it into this three-dimensional surface. So this rectangle is going to live somewhere else, u, v, instead of x and y, to differentiate. And so we're going to find a function which we typically are going to write as r. And then we are going to integrate, instead of integrating over the surface, eventually we can integrate over this rectangle, which is going to make things way, 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 way simpler and easier. So our goal eventually is to be able to come up with this over these surfaces, but it will be a lot easier if the surfaces we were integrating over were just rectangles or even circles. We have polar coordinates, so if we have some kind of circles in polar coordinates, or rectangles in polar rectangles, what I call polar rectangles. So if we can do this or something like that, that would be way, way, and we're still going to label this as U and V. If we have something simple enough, then we can make our work way, way easier. So right now, parameterizing consists on this part of this diagram, going from rectangles or circles into something that is more complex in 3 dimensions. Yeah, essentially what we are doing is taking a sheet of paper. Yep. So I'm just going to take a sticky note. Yep. So pretend that's this, and then we're going to transform it via R and come up with something that is going to be maybe this. Yeah, and we're through the transformation, things are going to shrink or stretch. So pretend you have more like a rubber band or a little rectangle that you can actually change into something like that. Of special interest, we will have circles. So circles and spheres, for that matter, are of special interest. Special interest to us. So first, I'm going to show how to rotate a point. And then we're going to go from there. So pretend you have a point. So this is going to be an example 1, but it will have many parts to it. So A, we want to rotate. So 2, 3, 0, a point in 3 dimensions around the x-axis. Yep. Around x-axis. So we want to come up with a u function, rather an r function, that creates that rotation. Let's see. So these are going to be paths. And then we're going to, in the second example, we're going to go to surfaces. So we're going to practice with paths or curves. So curves first. Yeah. So we have a point, 2, 3, there it is. We want to rotate it around the x-axis, so this axis. And yep, we can rotate it this way and create a circle. The radius of the circle, of course, will be 3, because the circle will be 2 units out and then 3 units to the point from the x-axis, and then rotate, and then we have a circle of radius 3. The way we do that is, well, the 2 is going to stay where it is. So we're going to have an r of t with 2 as the first coordinate. And then on the y coordinate, we want to start with 3. So we put down 3 cosine of t, okay, because the cosine of 0, we want to start with t equals 0 here at that point. And then we want to have a lift on the z so that it goes from 0 to 3, back down to 0 as we go around, then to -3, and then back to 0. So 0, 3, 0, -3, back to 0. Well, that sounds just like the sine function, 3 sine of t, and that does the job. So if we want to rotate the point 2, 3, 0 around this x-axis, so the x-axis is on the center of this circle, that's the way to do it. Keep the 2. Now, the point initially did not have 0. That is very important. Did not have a non-zero number on the z's. And we are putting the 3 and the sine to create this upper motion. Okay, B. Rotate 2, 3, 0, same point, around y-axis. Okay, so we start with the same point, 2, 3, there we are. And now we're going to rotate around the y-axis to get this circle. So the y-axis is the center, and we're going to go around this circle. And we want to know how to go about doing that instead of rotating around the x-axis. So same starting point, 2, 3, 0, but now we're going to rotate. So the y value has to stay constant at 3. So this is a different r of t than the one up here. I'm not going to distinguish it with R1 or R2. I guess we could put RA, RB, but I'm not going to do that. So the second coordinate will be 3 because we want the y value to be 3. Just like up here, we wanted the 2 value, the x value to be 2 and stay 2. Otherwise, the circle is not going to be vertical. So we want the y value to be 3. We're going to put 3 in the y value. So we're missing the x and the z. All right. The x, we wanted to start at this point already, which is going to be 2 units off the y-axis. So that is going to be 2 cosine t, y cosine, because that is going to create a 1 when t starts with 0. Oh, I missed one thing up here. In this answer, t, I just as well write it down, will go from 0 to 2 pi. Yep, and that creates a circle. Starting with t equal to 0 here, going all the way around and coming back to the same spot. And so we want to start here. Oh, and the circle is going to go in this direction. This one is going to go in this direction because we want to start with this point and then move upward in the z direction. And as t increases, we know that the sine of t also increases initially. Of course, later then it's going to go down. So we can put 2 sine t. Okay, start contrasting these examples because it is important that you know what is going on. Because, for instance, here we kept the 3 constant. I'm sorry, we kept the 2 constant and the 3 showed up twice. Here we kept the 3 constant and the 2 showed up twice. I'm going to rewrite this a little more cleanly. So we have 2 times cosine t, 3, comma, 2 times sine t. There we go. So that rotates the point 2, 3 around the y-axis. Okay. C, we want to rotate. Now let's find a new point. 2, 5. What I meant by that, 2, 0, 5. So this point is on the xz plane, on the xz plane. So 2, 5. So there, and we want to rotate it. Let's start by rotating it around the x-axis. Around, you can rotate around anything you want, but we're choosing the x-axis, around the x-axis. All right, so we start, so what is going to be constant? 2, again, as in this example, the 2 is constant. All right, so r of t. Sorry to interrupt myself, but I forgot to mention here that 0 is less than or equal to t, less than or equal to 2 pi. Again, if we want to have a full circle. The full circle is going around this way. So again, we're going to have a fairly large circle because the radius is going to be 5. So 2 remains constant. We want to we want to start at that point, and we want to rotate this way. It's going to be a fairly large circle. So it's going to go around and coming back this way. And we are going in this direction. So the z starts with 5 cosine of t, and then there's no depth initially. We want to put some depth in the y direction, and so but we want to little by little put in the depth in the y direction, in the positive y direction. So that's why we will have 5 times sine of t, but we want to already start with the 5 on the z direction. So 5 cosine of t will do. And again, 0 is less than or equal to t, less than or equal to 2 pi. Yeah. So, yeah. So 2 is fixed. Sine is on the second component, while cosine is on the third. Look at this other one, cosine and sine. So it's interesting the way we start. So we start in example 1a, we start at this point and then we go around this way. Here we start on the xz plane and then we go on the other direction. Same kind of circle because they're both vertical and they're both perpendicular to the x-axis. However, this one starts out here on the xz plane, while this one starts out on the xy plane. This one goes on the counterclockwise direction, seeing it from our point of view, while this one goes on the opposite direction. All right. Let's take this point and now turn it around. I'm going to try to squeeze that in here. So do we want to do that? Maybe. So we want to rotate this point here. Same point, but now we go around the z-axis. Let's try to squeeze it in here, D. So rotate 205 around z-axis. So that's going to be example D. R of t is equal to, okay, so we want the z to be constant because we're going to be going around at 5. The radius is going to be 2. We want to start out with an x of 2. So that causes 2 cosine t. And then we want to have some depth in the y direction. So that causes us to have 2 sine t. And then we want the 5 to be constant. So make sure you know how to play around with sines and cosines and the numbers so you get your rotations correctly. How about a point that is on the YZ plane? So let's move on to example 1, A, B, C, D, E, 3. So 1, E, because we just did D. So rotate. Now we're going to pick a point that is on the YZ plane. So let's say 3, 5 around the y-axis. Y-axis. Okay, so 3, 5 is about there. We want to rotate around the y-axis. So we want to have a circle that goes around this way. Okay, so we want the y to be constant. We want to start at this point with an x of 0. At that point, 0. So r of t, we want it to be 5 times sine t. The y has to be constant at 3, and then 5 cosine t, and that will create this as t goes from 0 to 2 pi in this direction. 1f, example 1f, what if we want this to rotate this way? So then, so rotate 035 around z-axis. Okay, at this point, I suggest you pause the video and see if you can come up with it on your own before I do it. So I'm going to assume you paused, or you can pause right now. Okay, now we're back. And so let's see, r of t will be, okay, I want to start at that point. So the x has to increase. So we're going to, but what is the radius? 3, okay. So 3 sine t, comma, the y, we wanted to start out with 3 cosine t, and then 5. And that will create this circle, yeah, that is going to be floating at a level of 5 units from the origin, above the origin. And it's going to go around this way. Again, t goes from 0 to 2 pi. It is important to know your domain of the function. And I was going to leave it at that, but probably somebody's going to think, wait a minute. So let's do one more example. What if we have the point 2, 3, 0, 2, 3, 0, and we want to rotate it around the z-axis? That's going to be Um, okay, see, because those points are lined up with the x-axis, the y-axis, or the z-axis, the points that we picked in examples 1a, 1b, 1c, 1d, 1e, 1f, the radius of the circle was pretty straightforward, again, because things are pretty lined up nicely. This one is not lined up with, um, actually, let's take one point higher than that here. So how about 2, 3, 5? Yeah. And we want to rotate it around. This is going to look a little better, I think. And we want to rotate it around the z-axis, just to pick one. You can pick anything. This one is more difficult. Um, not not a lot more difficult to do, but it is a little more challenging because neither one of those numbers will be the radius. We have to figure out the radius, which is the distance from the axis of rotation to the point, which is the same thing as here. We take it down here or there. It doesn't matter. So the radius is going to be, well, the hypotenuse of the triangle 2, 3 on the two legs, the right triangle. Um, so of course we got 3 squared, which is going to be 9, plus 2 squared, which is 4, and that gives us 13 when we add the square of the 2, but then we got to take the square root. So that is the square root of 13. So the radius of this circle, the radius is going to be square root of 13. All right. And we want it to go around this way. See, I think it would be difficult to start there. Let's start it. So let's take this point on the circle and start here and go in this direction. Or you could take the other point down there. So one possibility. So rotate. The problem is rotate 2, 3, 5 around z-axis. Okay. So if we want to rotate, starting at this point, not at this point necessarily, one possibility we could do is to have, so we want x to start out with that. So we have square root of 13 cosine t, comma, and then get to here. So the y value is going to be square root of 13, comma, sine of t, comma, and then this is going to be leveled at 5. So just keep the 5 there. Okay, so that will do it. The problem with this, it's not a problem, it is just a circumstance, is that this circle will go through this point as desired, but it will start here. If you wanted to start there, then you would have to figure out, you have to shift the t, so that we actually start there. Let's see, this angle on the bottom that corresponds to this point up here would have an arc, a tangent of 3 over 2. 3 over 2. So if we want to shift, we would have to do this. Okay, so this will do. Let's do an R1 and an R2, a different one, with a shift. Start with square root of 13 cosine, okay, of the arc tangent of 3 over 2, close the parenthesis of the cosine, comma, square root of 13 sine of arc tangent of 3 over 2, comma, 5. So that will do it. Now let's double check. So that is the angle, this angle, and that will start at that point when, sorry, I meant a shift. This is not a shift, this is just a point. This would be this point. Yeah, this is cross that. This is just, if you do this, you will end up with 2, 3, 5. Yeah, because the cosine is the adjacent. Yeah, 2, 3, 5. Adjacent over hypotenuse. Yeah. So this is just the point. Yeah, this is 2, 3, 5. Yeah, but we want to start there. So the R2 of t actually will be square root of 13 cosine of t, take away tangent inverse of 3 over 2, there we go, comma, square root of 13 sine t, take away tangent inverse. I'm going to adjust this in a moment. I think we don't take away, we add over 2, comma, close parenthesis, 5, close parenthesis. Okay, that was a squeeze. Now let's double check. When t is equal to 0, those numbers are going to be negative. So we really want to start with plus, plus, and as t increases, we're going to add to the angle. So I think that will do. If we have those, that will actually start at 2, 3 and go around and continue being drawn this way, if you wanted to do it that way. That's why, but most of the time, we're not going to start at a point like an odd point. So this is an oddity in our work. It won't happen this way. This is a curiosity in the work we are doing. Some students might be asking, well, that wasn't too bad if the point lines up, but what if the point doesn't line up in the plane, in one of those two planes, if we want to rotate with respect to the z-axis? We have to make some adjustments to figure out the radius, and we want to make even a further adjustment to figure out the angle, but we can do it. It can be done. So this is an oddity. Yes, let me just make a note. Example 1G is an odd example. And by that, I mean it's not an example that we typically do in this class. But it can be done. 4. Okay. So example 2 will be about parameterizing a unit sphere. Okay, and we're going to do it in 2 ways. So 2 ways. All right. So first, we're going to create a half circle. And then we're going to rotate each one of the points around the x-axis. So we're going to create a half circle, and then we're going to rotate each one of the points completely around the x-axis, and that is going to create a sphere. I'll show you in a moment, but okay, so, and we're going to use a variable u to rotate. Now, the R we're going to build will have 2 components, u and v. I'm not going to put the v in the picture yet, because the v will do the rotation around the x-axis. So for now, let's keep it as 0. But it will be, eventually, will be uv, not just u0. I just want to do this in parts, one thing at a time. So that's why I'm focusing on the u. And this is going to be a surface. We use the same r, but this is going to be a surface as opposed to an example 1 where we had a curve. You know, those circles are curves, closed curves. Anyway, so pretend you start with a point 1, 1, 0, 0, and we want to rotate around the z-axis. Remember, we did this. It's just pretend, it's an easier point, but because it already starts on one of the coordinate axis. So this is 1, 0, 0, rotate around the z-axis. So that means we're going to put 1 cosine of u, 1 cosine u, comma, and then the y is going to be 1 sine u, and for now, 0. We shouldn't put the 1s, but I want to emphasize that the radius is 1. Okay, so that creates, by changing u from 0 to pi mind. Now we're going from 0 to pi to create only half of the circle. We don't want to do the whole circle. Why not? Because now we want to go and take each one of these points and rotate them around the x-axis. Now, this point is going to be farther out. So that's going to rotate around the x-axis and around the x-axis and so forth. So all of those rotations are going to create a beautiful sphere. I can't believe I just said beautiful. A really, really nice sphere, a round, smooth sphere, as we take every one of those points and rotate around the x-axis. Now, remember how we rotated around the x-axis. Um, let's see, example 1a. Remember, we had a point 2, 3. So pretend you got a point cosine u, sine u, somewhere in here. And we're going to rotate that point around the x-axis. So what we did is we kept the 2 as is. And then we have something and 0. And that's something we put cosine of the variable. And then we reproduce the same kind of setup as in here, but with the sign instead. Okay, so we kept the 2, the first coordinate, fixed, which makes sense because the circle is parallel to the YZ plane. So keep the first coordinate first. On the second coordinate, add cosine. Okay, so now we're going to create a second dimension. So R of UV will be, keep this guy as is, cosine U. To this one, we're going to include a cosine of V. And that, so the U creates this arc, and the V creates, for each one of those points on the initial arc, a whole circle. So we're going to have sine U, cosine V, and then for this part, remember, this is like cosine of t. That cosine of v is the taking the place of the cosine of t, and the sine u is taking the place of the 3. So now we're going to have sine u sine v. Sine u sine v. As u goes between 0 and pi, and as v goes between 0 and 2 pi. So this is what we've done. We have taken a rectangle in the UV plane, U, so it's a shorter rectangle this way. So we go to pi, so only 1 pi this way on the U's and 2 pi on the V's. And we have taken this, and with the help of R, we are able to turn this rectangle into a ball. Let's put the x-axis here. So this is a whole ball. And then the x-axis comes out there, okay, through the center. So this is just the x-axis. I don't want to draw the y-axis, but there's 2 endpoints. Now, this line, when u changes and v is 0, creates this line, the initial half circle. All right, each line that is parallel to that will create another half circle, but it's going to go around this way. You know, they're going from this pole to this pole. Yep. Every line that you do that every horizontal line, whoops. So eventually they're going to go down this way. Yep. Every one of those lines will create not parallel lines, well, because all of those lines are going to go through this pole and the other pole, the x, where the ball intersects the x-axis. Vertical lines, I'm going to make a bigger rectangle this time because u goes up to pi. So that's u. And v goes up to 2 pi. There we go. So it's the same rectangle. I just made it a little bigger. Vertical lines, on the other hand, will correspond, and I'm going to draw the ball again. So there's the initial half circle, and then vertical lines are actually full circles like so. So those are vertical lines. What essentially we have done is taking this vertical, pretend this is pi by 2 pi, and what we have done is fold it, that's the going around, fold it into, and while actually this is not the order in which we do it, but fold it and then squeeze this end and squeeze this end to create a nice sphere. That's what we have done. Yep. So all of these points on this edge collapse into this guy. So we are deforming the geometry of this. Yeah. By doing this, we're deforming it because you cannot really take a rectangle without breaking or stretching or shrinking anything and put it into a sphere completely. We cannot do that. So really, we kind of have done this. We take this and then collapse this end into one point, collapse all of this side into one point. So now we have the top and bottom, and then stretch that around the whole sphere. Yeah, it's kind of neat to see how we can modify using mathematics a rectangle and turn it into a sphere. By doing so, we are collapsing things. And so this is not going to be a one-to-one, a perfect one-to-one map or function, because all of those points on the edge are going to be mapped into one point. Those are the only points in the two edges. For purposes of integration, that won't matter because the double integral of curve is going to be 0. Yeah. So we're going to lose or add zeros to things. It's like the area of a point, a mathematical point, that which has no depth or a point that has no length or height or anything. We draw it, and of course this, if you zoom in, will have some area, but we are representing something that has no area, an actual mathematical point. So that's kind of how it happens. This was 2A. And by the way, if you recognize this a little bit, this is the way they do spherical coordinates. You probably remember in spherical coordinates, they use phi and theta instead of u and v. Yeah, phi and theta. And they don't use this semicircle. They use a different semicircle, I think one that is vertical, and then they rotate around the z-axis with, so phi draws the initial semicircle, and then we rotate. So this is not in the correct order, but it's a good idea for you to visualize how spherical coordinates, this is exactly spherical coordinates, but from a different point of view. So it would be good to compare this with what we have done before with spherical coordinates. Let's do B. Okay. So again, we're going to parameterize. Again, parameterize unit sphere differently. Okay, so this is what I'm going to do. We're going to take a whole circle, a unit circle, and that is going to be defined by u. So r of u0, just to draw this curve, is going to be, okay, and you know how that works, cosine of t, sine of t, and then we have 0, because that's flat on the xy plane. Okay. Now we're going to do the same thing we did. We're going to rotate each one of the points around the x-axis. Now, before I continue though, u this time will go from 0 to 2 pi because we want the full circle. Now we want to, so start with a full circle, and rotate it to create the sphere. Start this way and rotate it. Now, when we rotate it, there's a back of the circle. See, what we did here was a semicircle, only half of it, and we rotated it all the way around to create a full sphere. Well, if we want to create a full sphere here, we have a full circle to start with. So the top, let's call this the top of the circle, rotated, has to be rotated only halfway because the bottom is going to rotate underneath. See, we have this situation, we're going to rotate, and it's only sufficient to rotate 180 degrees instead of a whole 360 degrees to create the sphere. If we rotate 360 degrees, then we're going to create in the sphere twice. We're running over the sphere 2 times. So our UV, okay, so now we're going to take each one of those points as we did earlier and rotate them around the x-axis. So we're going to have cosine of t, that has to stay, that's the x value, and then sine of t, oh, I don't know why I put t, that's supposed to be a u, that's a mistake in my part, because I was thinking of a curve, that's why. So this is u, sine of u, and then cosine of v, comma, and then this guy becomes sine of u again, but multiplied with sine of v. And you're thinking, wait a minute, didn't we just do that? Cosine u, sine u, cosine v. Yeah, that was exactly the same thing. The difference, though, is that now we go on the v's from 0 to pi, and that makes a gigantic difference. So though, yes, it's a huge, huge difference. So we're taking this rectangle now, 2 pi on the u's, pi on the v's. You know, the origin is here. We're creating it. We're creating the, this is so weird, I think, because there's the sphere. Okay, from here to pi, we have this half. From pi to 2 pi, we're going to end up with the other half comes around and connects here. All right. But here's the weird part. This line is going to draw a half circle because we only go to pi. And to find the continuous other half circle that goes down here and connects back there, you have to come on this line. So those two lines create this circle. And then to do the same thing here, you gotta go up one, down the other. So this is kind of what we're doing. Okay, we start with this, split it in two, but still connected. Let's see. Yeah, draw the circle. So this is the initial circle around, and then use this part to cover one end and use this part to cover the other end. Oh, my hands are kind of on the way. Again, cover this and then cover this other end with the other half. So first we have to take the rectangle, split it in two, create this circle with the connected portions, cover one, cover the other side. This is not desirable, and that's why people don't use it, even though it does work. It will work. We will have a nice sphere, and everything will be pretty well defined, except we don't have continuity. And continuity is very important in calculus, extremely important. Continuity of a function. See, you go this way, you know, up this way, and then you got to stop. If you want to continue, you got to, with the same circle on the sphere, you got to come back. You got to jump all the way out here and then go in the opposite direction. No, no, no. I even lied there. You got to jump from here to here and then still go up. Yeah, yeah. It's a mess. Because we end up breaking the rectangle to create the sphere versus the example 2A where the lines don't break. The lines on the sphere don't break up. Everything is nice and reasonably smooth. So that's why they don't define spherical coordinates this other way. You may be thinking, wait, didn't we just change the u and the v because uh, here the pi is, the u can only go up to pi and the v can go to 2 pi? No, 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 no. There's more to it. The way this is drawn breaks continuity. So this is, unless you're only working with the top or with the bottom, this is not a desirable way to do calculus, because the integrals have to be broken up into parts here. Things are not going to be as smoothly, I believe. Yeah. So we have to pay attention to continuity when we are parameterizing. Most of the stuff we're going to be doing will parameterize reasonably easy. Oh, next, let's talk about areas of surfaces that have been parameterized in general. Okay, so the general formula for the area of a surface, just a generic surface that has been parameterized. So we're going to assume that the surface has been parameterized, even though the surface is an x, y, z. So we have some kind of weird, perhaps, yeah, some kind of really weird surface. So this is S, but that perhaps came from a nice rectangle or a nice, some kind of circle using R, but this rectangle is U, V, and this one is in X, Y, Z coordinates. So the way we do this is by taking the double integral over this surface, D, of the magnitude of R sub U, so the partial derivative of, rather, the derivative of R with respect to U, cross product with RV magnitude, dA, where the area is again taken over the UV plane, over UV plane, and this is the whichever region on UV plane. Yep. Yep. So that makes things way easier. This is a new formula. The reason for that, pretend you got, again, some kind of surface and you got R at a point. So the partial derivative will give you a vector here. And by the way, we're deforming, by using R, we're deforming a regular rectangle into trapezoid. No, not a trapezoid, a parallelogram. There we go. So, and the parallelogram in general will have those two sides, which are going to be R sub U and R sub V, not necessarily in that order. Who knows where they're going to be pointing, R sub V. And then the area of this guy is going to be the cross product of those two, which is the perpendicular vector. So instead of adding those little guys, we're going to be adding, that's why we're going to be adding the cross products. Yep. Yep. And then this would be a 1 unit by 1 unit, but eventually we want to do dx and dy, and so, or du rather, and dv So then we multiply by those corresponding du and dv, and that's why we need the area. So that is the general reason why we have this formula. And we want to have the magnitude, because otherwise we have a vector. Doesn't make sense to add a bunch of vectors and like that in this case. So we want the magnitude to actually obtain those little areas. So again, what is happening is that the rectangles here are deformed. They're not nice squares, and that's why we need to do the cross product. Okay, as an example, example 3, find the area of the unit sphere. Okay, so the unit sphere, we're going to piggyback on example 2, where we found example 2a. Okay, r of uv is the cosine of u, sine u, cosine v, sine u, sine v, where u goes from 0 to pi and v goes from 0 to 2 pi. Can we flip those two? Sure, but then the continuity is not going to be nice anymore. Things may or may not work. I don't want to risk it. So I'm not saying that in this case they won't work. It could be that they don't work because, again, we got rupture of the domain to create the sphere, and that could cause an issue. So we got to pay attention to those little details. Okay, the formula that I just gave is here. So we need to find r sub u, r sub v, cross them, magnitude, before we can even start the integral. So there's a process involved in this. So let's find r sub u. Okay, derivative of cosine is negative sine of u, comma, derivative of sine is cosine of u, keep the cosine of v because that is constant with respect to u, comma, again, cosine of u, and keep the sine of v. R sub v, okay, so that's going to be 0, comma, derivative of cosine is negative, keep this sine of u, but now we have the sine of v, comma, derivative of sine is cosine, sine u, cosine v. Okay, we're going to do ru cross rv. Okay, so that's going to give us a vector, and we start with those two. So sine u, cosine u, and cosine of v squared. So sine u, cosine u, and then cosine squared of v. Okay, instead of trying to crunch that into one line, I'm going to put the 3 components in 3 lines. I think that will be more reasonable as far as writing things out. Okay, so then we have those 2 multiplied together as the second component, and there with an extra negative because of the way we do the cross product, but this one already has a negative on it. So we're going to end up with a sine u squared and a single cosine of v. So sine square of u, sine times sine is sine squared, and then just cosine of v. Okay, I guess we can put 2 components on the next line. And then multiply those 2, and we're going to have sine squared of u, and then sine of v. Okay, so that is the cross product. Next, according to our formula for the surface area, we found the cross product, magnitude, So the magnitude of RU cross RV is going to be, okay, let's see, we're going to have a square root. We're going to square this guy first. So we're going to have sine squared cosine squared, sine squared U, cosine squared U, cosine to the 4 of V plus sine to the 4 of U cosine squared V. And I'm going to continue this sum here, still under the same root, plus sine to the 4 U sine squared V. Okay, now those two terms, the last two terms, have a common factor, sine to the 4 of U. So we can factor out this sine to the 4 of U, and then we are left with cosine square of V plus sine square of V. And those are going to add up to 1 after we factor out the sine to the 4 of U. So we're going to end up with sine squared U cosine squared U plus, oh, no, I missed the cosine here. Cosine to the 4 of V plus sine, this looks a little funny to me, sine to the 4 of U. Let me pause for a moment so I can check. Okay, I almost immediately found a mistake. When I did the cross product here, this seems to be correct, but then I missed to do the cross product here. I mean, there's another product missing here. So we have to add sine U cosine U sine squared. Sine U cosine U sine U cosine U sine of V squared. Sine squared V. That is the first component only of the cross product. So there is a plus here. Okay. And then the other two components seem to be correct. Now we have sine U cosine U sine U cosine U, which may be factored out. What is left? It will be sine squared of V and cosine squared of V, which add up to 1. So we end up with sine and cosine of U only. Sine and cosine only without this guy. So this should go away because, again, in my initial cross product, I multiplied those two and I missed multiplying those two. I think that will fix that. And then here we scratch that off. Yep. And now I think we are good. So then this is equal to the square root sine squared may factor out. And then we have another sine squared because we got 4 of them plus cosine squared of the same angle, of the same input, U. So that's going to be 1. Now, technically speaking, that should be the absolute value of the sine of U. But I'm going to put the sine of U because U goes between 0 and pi. And consequently, the sine of any one of the inputs between 0 and pi is going to be positive or 0. So let's make a note of that. Equals just the sine of U. And the reason for that is because sine of U is greater than or equal to 0 when U is between 0 and pi. So we are allowed to do that because this is going to be positive anyway. Okay. So now what? Oh, we want to find the area. So the area of the sphere is going to be the double integral of the sine of u. Does that look familiar? It should look familiar because with respect to the area, so du dv, and remember what we did with this transformation is we took a vertical rectangle from pi 0 to pi and 0 to 2 pi on the u's and the v's and transform it into a sphere, a unit sphere. Yep. So the double integral goes as u goes from 0 to pi and v from 0 to 2 pi. So the antiderivative of sine with respect to u is going to be negative cosine. So we're going to have negative cosine of u from 0 to pi. While that is happening, or after that happens, then we're going to take the integral from 0 to 2 pi. If you factor that out, it will work out anyway, but I'm going to keep it the way it is. So from 0 to 2 pi, so we have cosine of pi, which is negative 1. Additionally, with this negative is going to make a 1 plus, because we're going to subtract, but then there's another negative here. So we have 1 dv, that's going to be 2 constant, and then multiply by 2 pi. So that is going to end up being 4 pi. So the area of a unit sphere will be exactly 4 pi, no more, no less than 4 pi. Whoa, that was an interesting problem. Example 3. The reason why it became a little more difficult is because those vectors were fairly large. We got to do the cross product and carefully, and then we end up with this, which we integrate. The actual integral was not bad at all. It was actually pretty straightforward. The problem was in this case to figure out the cross product correctly. Example 4. How about the area of a sphere of radius a? So same problem, except that we're going to have a sphere of radius a. And I'm going to actually piggyback on this. So r will be the same, except that we will include a, or you can just factor out the a outside. So we're going to have a new r. I'm going to label it as r2, which is going to be the same as a, that's a scalar, multiplied with r1. Okay, with r1 as in example 3. There's no point in redoing everything if all we have is a, an extra constant. So the a is going to be attached to this, and this, or you can factor it out and keep it outside. Probably we can keep it outside. The derivatives are going to be the same, except that there's going to be an a in it. So r2u, so the derivative with respect to u is going to be a r1u. r2v is going to be the constant r1v. So when we cross those two, r2u cross with r2v, we're going to cross A, R1U, cross with A, R1V. Okay. But we know that the cross product works in such a way that we can factor out the scalar factors. So we can factor an A and another A. So we're going to end up with A squared, and then R1 sub U cross with R sub 1 sub V. I'm just labeling R sub 1 as opposed to just R because there's going to be two R's involved. The R2, which is a new R, and we're not using exactly R1, we're modifying R1 by a factor of A. Okay, so the magnitude of R2U cross with R2V, magnitude, is going to be the same as A squared times the magnitude of R1U cross R1V. I'm just telling this is the example 3 as opposed to example 4. But we know what this is. This is sine of U. So this is A squared sine of U. So we're still integrating sine of U, and we have the same parameters, the same going from 0 to pi on the U and from 0 to 2 pi on the V. The only difference is that we have an extra A squared. Yep. So the area of the surface is initially the double integral of A squared sine U du dV from 0 to pi on the U's, from 0 to 2 pi on the V's. But the A squared factors out. Once it factors out, then we end up with this, which gives us 4 pi. So we end up with A squared times 4 pi, which is 4 pi A squared. 4 pi A squared. So that is the area, the surface area of a ball. Yep, of radius A. Yep. If you didn't know that, now you know it. And you can check that by using calculus 2 means when we have, because a ball is really a semicircle rotated. So there's a couple of ways to double check that this is correct. That is the correct answer. But now you have a way to figure out why it is so. Okay. That was example 4. I want to keep track of my example numbers. And now before we do example 5, let's talk about this. There's what is called a trivial parameterization. Trivial parameterization. So R of U V, if you just take U and put it in the first coordinate, V on the second coordinate, and then whatever function of UV on the third component, then we're not really deforming the surfaces. So the goal of parameterization is to hopefully start with a nice region and change it into a region that perhaps is going to be, or a surface that is going to be really, really weird, with maybe round or curves, or curves in all different ways. Yep. But if we just use U and V for the first two coordinates as the way they are, then really what we have is just the region here, which may or may not be a nice rectangle, and then F up there, as we've done before. There is no the parameterization is trivial. What trivial means in mathematics is that it doesn't add something new, such as being able to change a weird shape into a nice shape. This is already going to stay the way it is. So that's what we mean by trivial. doesn't add new things, doesn't break things down into pieces, each one of which could be simpler. Yeah, so that's what we mean by trivial. Oftentimes, if we have a trivial parameterization, instead of using u and v, we simply use x and y, because those are the values we're using anyway on the first two components, f of x, y. So this is what we call trivial parameterization. If we're not changing anything, just keep it as x and y, then keep it. So the question is, what is the surface area on the trivial, if we use a trivial parameterization? Well, we use the same formula. R sub x, which would be R sub u, same thing, is going to be 1 O f sub x. So 1 because the derivative of x with respect to x is 1, 0 because the derivative of y with respect to x is 0, and then this one. R sub y is going to be 0, 1 f sub y. If we do the cross product, R sub x cross R sub y, we get, let's see, minus or negative f sub x, comma, negative f sub y, comma, 1. If we find the magnitude, we get the square root of this quantity squared, but the negative goes away after we squared, plus f sub y squared, and then plus 1. Thus, if you just have a regular x, y, z function, then the area of that surface is going to be the double integral over the domain of the square root of f sub x plus f sub y, each one squared, plus 1 dA. So if you just have a regular z equals some kind of function of x, y, we may apply that and obtain the surface area of that. So let's do example. Again, I want to keep track of the examples, example numbers, example 5. Okay, so z is equal to x squared plus y squared. Find the surface area within the unit circle on the x, y plane. I was just checking that I was actually recording this. It would be weird for me to do all of this without recording. Example 5. I always get paranoid about that. So this is a familiar paraboloid. And then within the unit circle on the x and y plane, so we're going to end up with this. Okay. So according to the formula we just showed, what we want to do is find z sub x, which is 2x, z sub y, which is 2y, the derivative of that with respect to x, and the derivative of that with respect to y. And so the area, the surface area of this paraboloid within the unit circle will be the double integral, and let's call this d. D would be the whole circle over d of square root. So this guy squared, 4x squared plus 4y squared. We need to add 1 dA, again, with respect to this area. So this is an application of parameterizing surfaces, how to find the area of this. We could go from, we could solve, so the equation of the unit circle on the plane would be x squared plus y squared equals 1. And we could solve for y and have, plus or minus the square root of 1 minus x squared, and we can have a double integral going from the negative to the positive with respect to y, and then from -1 to 1 on the x's, and then go through and that will be painful, I think. That wouldn't be trivial. So instead, we're going to change to polar coordinates. So in polar coordinates, we know that x squared plus y squared is r, but be careful. Yeah, x squared plus y squared equals r. But you may be thinking, wait a minute, it's 1. Yeah, it's 1 on the boundary, but not 1 inside. It will be a generic r. It could be 0 or what half. Inside of the region, r will be changing. So change to polar coordinates, and we'll have, again, x squared plus y squared is r, so that is really 4r squared plus, actually r squared, not r, plus 1 with respect to r and with respect to theta, as r goes from 0 to 1 and theta goes from 0 to 2 pi. We are missing something, and I'm going to give you 1 second to tell me what we're missing in this integral. 1. We are missing the, starts with a J, Jacobian. Every time you change variables, and we're changing from XY variables to polar, we need a Jacobian. You can put the Jacobian anywhere as long as it is inside of the integral. So the Jacobian will be R. That's going to cause this integral to go way, way better. First, because we have constants, as opposed to, I didn't write it down, but remember we had the square root, the top negative square root and positive square root. In addition to that, this R allows us to do a nice change of variable. We can set u to be 4r squared plus 1. So du equals 8r dr. Yep. So the integral is 1 over 8 because of this 8. Integral from 0 to 2 pi. Integral from 0 to 1. Nope. I'm going to change that. It's not from 0 to 1 anymore because we are going to have du. Where is it? There it goes. So not from 0 to 1 on the u. So we have the square root of u du d theta. But u, when r is 0, will be 1. So we go from 1. And when r is 1, then u is 5. Yep. So 1/8 integral from 0 to 2 pi of, well, that's going to be u to the 1/2. Integrate that, and that gives us u to the 3/2 over 3/2, 2/3 u to the 3/2, which is the same thing as u square root of u. Oftentimes I write u square root of u for u to the 3/2, same thing. I think it looks a lot better this way. I would prefer if you did that too in your problems, from 1 to 5 d theta. Okay, so we are going to plug in 5. The 2/3 factors out and simplify with the 8. So we actually have 1 over 12, I believe. And then we're going to put yeah. And then we're going to still integrate from 0 to 2 pi. And we're going to have a constant here. It's 5 root 5 minus 1. When you plug in 5, you get 5 square root of 5. And when you plug in 1, you get 1 square root of 1, which is still 1. The theta. So this is a constant, can factor out. We're going to end up with 2 pi with the 12 simplified down to pi over 6 times 5 root 5 minus 1. Make sure that is in parentheses. And that is the exact area of this surface over this disk. We could double check example 5 by means of a calc 2. So again, um, you got this, and this is generated by y equals x squared. This, if we rotate around the y-axis, this is on the x-y-axis, we're going to generate this paraboloid exactly correctly. And it is going to be generated over the unit circle because we're going to go from 0 to 1 on the axis. So using calculus 2, so we're going to figure out the area of this surface by using calculus 2. This surface happens to be a surface of revolution, so we can split this into bits like that are revolved. So the area of the surface is going to be the single integral. Okay, so this distance is x, so 2 pi x accounts for going around. Remember how we did this in calc 2? We split this into strips. So we have bands that kind of look like this. So they go around 2 pi the radius, but the radius is x in this case, and so that accounts for the length of this. And then we have to integrate with respect to not y. Initially, I was thinking, ooh, dy, but that is not true, ds, where s is the length here. And this is going to be over the as x goes from 0 to 1. This is kind of weird notation. I don't advise you to do this, but as x goes from 0 to 1. All right. Perhaps, anyway, let's do this. So we have 2 pi x. Remember how we find ds in calc 2? You take the square root, and then you do the derivative of this guy, square it. So again, that is going to give us 4. The derivative of x squared is 2x. When we square that, we get 4x squared plus 1 dx. Now we're good from 0 to 1. So a few things do repeat if you compare to the previous example. We're going to set u, again, to be 4x squared plus 1. du is 8x dx. So we need to divide by 8, factor out the 2 pi, which is a constant. And again, we have the integral of square root of u du from 1 to 5, because when x is 0, u is 1. When x is 1, u is 8. No, it's 5. So we pretty much end up with the same kind of thing, pi over 4 times 2/3 u square root of u from 1 to 5. Simplify, and we get pi over 6 times 5 root 5 minus 1, which is exactly the same answer we previously obtained. So this is one way to check. If we have a nice solid of revolution, then you can check the answer this way. If you don't have a solid of revolution, then it is not as easy to check the answer this way. Yeah. So practice, practice, practice. A lot of calculus books have problems about parameterizing and finding the area of surfaces. And just check them out and start practicing. And with this, we will stop this video today.